Welcome to our next video lesson. Today we are going to talk about acid and base ionization constants, which we use for weak acids and bases to help us determine things like pH and percent ionization. So if we take an acid and we put it in water, by a simple definition, that acid will dissociate and produce a hydrogen ion and then some anion. So we have a positive and a negative ion when we put that in water. So the acid ionization constant, Ka, is given by the concentration of H plus times the concentration of the anion divided by the concentration of the acid that hasn't dissociated. And all of those are included, they're all aqueous. And so all of those concentrations are included in the expression. And then because of stoichiometry in this example, we can tell that the concentration of H plus will be equal to the concentration of A minus. When we take a look at bases, since bases are proton acceptors or hydrogen acceptors, we show the general formula for a base reacting with water so that that base takes a hydrogen ion away from the water, leaving hydroxide behind. So this is a weak base dissolving in water to form Hb plus and hydroxide. So water here is a liquid. Everything else is aqueous in this case. So water is not included in our equilibrium constant expression. In this case, it's called Kb, our weak base ionization constant. So we've got the concentration of the base with the hydrogen times the concentration of hydroxide divided by the concentration of base. And so again in this reaction, the concentration of Hb plus is going to be equal to the concentration of hydroxide. Something that's neat to know about Kas and Kbs is if we look at Ka and Kb for a conjugate acid-base pair, so that's something like acetic acid and acetate, we can tell these are a conjugate pair because they differ only by one hydrogen ion. So acetic acid is an acetate ion and a hydrogen ion together, and acetate is just the acetate part of that. If we write the acid dissociation equation for acetic acid, if we put acetic acid in water, some of that acid will dissociate into hydrogen and acetate. If you take acetate and put it in water, some of the acetate will take a hydrogen away from water, which leaves us with acetic acid plus hydroxide. So if we wrote a Ka expression and a Kb expression for each of those reactions, they would look like this. So let me just cover that up a little bit. So for the acid, H plus times acetate divided by acetic acid. And for the base, we have acetic acid times hydroxide divided by acetate. It's really neat what you can do with these. If you take that Ka and the Kb and you multiply them, which you normally wouldn't want to do, but we're deriving an equation here. If we multiply Ka times Kb, we can cancel out the concentration of acetic acid and the concentration of acetate, and we are left with Ka times Kb is equal to the concentration of H plus times the concentration of hydroxide. And you've seen this before in our introduction to acids and bases, H plus times OH minus. You should be recalling what it is. That's Kw, okay, which at STP is equal to 1 times 10 to the minus 14. And so that means we can use this expression, Ka times Kb equals Kw, to help us find a Ka or Kb value. So for instance, if we knew the Ka value for acetic acid, if we could look that up, we always know what Kw is. We could find the base ionization constant for acetate, the conjugate base of acetic acid, using this equation here. So it can be a very useful relationship to understand. Hopefully it will be useful to you in your calculations.